In this lecture series, we'll learn about the radical halogenation of CH bonds. And in particular, we'll look at alkane halogenation and allylic halogenation reactions. We've already seen radical reactions in a cursory context when we learned about the different classes and types of organic reactions. Remember that radical reactions are reactions that proceed through reaction steps involving the movement of single electrons to break and form bonds. And often radical reactions are initiated by light. One of the most straightforward radical reactions is the radical halogenation of alkanes. For example, if we treat an alkane like butane with chlorine under irradiation with light, we break carbon-hydrogen bonds to form new carbon-chlorine bonds, leading to alkyl halides, or in this case, alkyl chlorides or chloroalkanes. And this halogenation reaction occurs through a radical pathway. Remember that radical reactions have three basic types of reaction steps: initiation, propagation, and termination steps. And we'll walk through those steps for the formation of the secondary alkyl chloride formed in this reaction. The reaction begins with the initiation step, which here is the homolytic cleavage of the chlorine-chlorine bond to form two chlorine radicals. Remember that we use single-headed arrows to show the movement of single electrons. Then, in the propagation steps, a non-radical species reacts with a radical species. In the example that I've drawn, the chlorine radical reacts with the alkane to abstract the hydrogen atom from the alkane and generate a new alkyl radical plus HCl. A second propagation step we could draw is the reaction of the alkyl radical with chlorine to form the alkyl chloride and the chlorine radical. And in this reaction, this is the most likely product forming step. Remember that the majority of product typically forms in a propagation step, not in a termination step. Then finally, in the termination step, two radicals come together to form a non-radical product. Here I've drawn the combination of the alkyl radical and the chlorine radical to form the alkyl chloride, and the reaction of two alkyl radicals to form an alkane. Remember that there are many other termination steps that we could also have drawn here. And although we only looked at the steps to form the secondary alkyl chloride here, the same set of steps occur to form the primary alkyl chloride. And in these reactions, both products form, and the ratio of the products depends on the stability of the radical. So let's take a minute now to look at radical stabilities. The stability of a carbon radical increases with increased substitution on the carbon, meaning that a tertiary radical is more stable than a secondary radical, which is more stable than a primary radical. And beyond that, benzylic and allylic radicals are some of the most stable radicals because the radical is stabilized by resonance. While a vinylic radical, one that places the radical directly on a double bonded carbon, is one of the least stable radicals. And this is the same trend as we saw for carbocations. And like carbocations, a carbon radical also resides in the p orbital of an sp2 hybridized carbon. A carbon radical, like a CH3 or a methyl radical, has 7 electrons, 6 electrons from the 3 carbon-hydrogen bonds, and 1 electron from the radical itself. So now coming back to the radical chlorination reaction, the secondary alkyl chloride is formed preferentially over the primary alkyl chloride in a ratio of 70:30, or 7:3. And that's because the secondary radical is more stable than the primary radical. So the secondary radical forms in greater amounts, leading to the preferential formation of the secondary alkyl halide. And this trend will hold for all chlorination reactions. A radical chlorination will form product mixtures unselectively, with the product ratios based on the stability of the radical intermediates. In contrast, a radical bromination, using Br2 here in place of Cl2, will proceed selectively with bromine adding to the more substituted carbon. So treating the same alkane under analogous conditions, but replacing chlorine with bromine, will lead to only one product, with the bromine replacing the hydrogen on the most substituted carbon. And because the reaction proceeds through a planar carbon radical intermediate, both stereoisomers of the product will form. Let's try an example. Predict the products that would result from the halogenation reaction shown. Because this is a chlorination, the reaction will be unselective and will form all possible alkyl chloride constitutional isomers. So to draw the products, we identify how many unique hydrogens we have in our structure, and then we will form that number of products, replacing each unique hydrogen with a chlorine. So first, we'll see chlorination at the methyl groups, and all 6 of the methyl hydrogens are the same, so they'll result in the same product here. Then we can consider chlorination at the tertiary CH bond. Chlorination at each of the CH2 groups will give 2 different secondary alkyl chloride products. And then finally, chlorination at the methyl group on the end of the chain will give the 5th alkyl chloride product. Again, because it's a chlorination reaction, all possible monochlorination constitutional isomers will form.